In this lecture presentation, we'll be reviewing the topics of probability and risk. As always, I recommend that you have the slides available so you can fill in the blanks and take notes on any material that is not covered on the slides as we move through the lecture presentation. Let's start by looking at probability and odds. Probability is a long-term prediction, and it is calculated by dividing the number of ways a particular outcome can occur divided by the number of possible outcomes. For example, if you were to roll one dice, and you wanted to know the probability of rolling a number less than 7, the probability would be 1, because all of the faces of the dice show a number less than 7. Therefore, the number of ways a particular outcome can occur would be 6, and the number of possible outcomes would also be 6. 6 divided by 6 is 1. Now, what if you wanted to know the probability of rolling an even or an odd number? For this, there are 3 even and 3 odd possibilities. Therefore, if you were to calculate the probability of rolling an even number, there would be 3 ways a particular outcome could occur, divided by 6 possible outcomes. This comes out to 0.5, which is referred to as maximum uncertainty. 0.5 represents an even probability of that thing happening or not happening. Lastly, what if you wanted to know the probability of rolling an 8? Well, there are no ways that this particular outcome could occur on a standard die. Therefore, the probability of rolling an 8 is a 0, which is to say that it cannot happen. Now, odds are a similar concept to probability, because odds indicate the probability of an event occurring. You may have heard odds in relation to sports, which they are quite often used to describe the probability of a team winning or losing a game. For example, 3-to-1 odds is the same thing as saying 3 out of 4 times the individual would win, or lose, depending on how it's stated. So if I said that the Angels had 3-to-1 odds to beat the Yankees in a game, that would be to say that if they played 4 games, the Angels would win 3 of them and lose 1. Now, what if we wanted to convert odds into a probability? To convert odds into a probability, the first number becomes the numerator, and the denominator is the sum of both numbers. So, using 3-to-1 odds as our example would be the same thing as saying 3 over 4, because 4 is 3 plus 1. Now, probability is expressed on a scale from 0 to 1, so we would need to divide 3 divided by 4 in order to get our probability, which is 0.75. Again, I want to point out that probabilities are really long-term predictions. Of course, rolling an even or an odd number at maximum uncertainty, we really have no idea if we will land on an even or an odd number. Same goes with flipping a coin. Events that have high probability of occurring are more likely to occur, but that doesn't mean that they will. Over time, however, the more times an event occurs, the more likely it is to match with the probability. So, if the probability were, let's say, 0.75, and that event were to occur over and over and over again, it is likely that over all of those trials, about 75% would be aligned with that team winning, for instance. It doesn't mean that in a series of 4 games, it's an absolute certainty that that team would win 3 out of 4 of them. Probabilities become more accurate over the course of time with multiple trials. Probability and odds influence our everyday life in many ways. They are the foundation of insurance companies. They're also used for weather forecasting, for risk assessment, to determine stock trades, to decide what move to make when playing cards like poker or blackjack, what team to bet on. Degrees of belief refer to the extent to which we stand behind our beliefs, and that depends on our perceived likelihood of a particular outcome. As humans, we have a universal need to find meaning, and that can hinder our ability to recognize chance events. Interestingly, a study by Loftus and Loftus in 1982 found that any two people sharing the same birthday is over 50% when there are 23 people in the room, and that number goes up to 75% when there are 32 people. So while we have this natural tendency to find meaning because it gives us a sense of order and coherence, much of life is actually random and up to chance. This also influences decisions, such as whether or not to spend money on buying lottery tickets. A Money Magazine poll that was described in your textbook revealed that people planning for retirement buy lottery tickets almost at the same rate as those investing in stocks. Interestingly, people also prefer to pick their own numbers, likely because it gives them an illusion of control and gives them a sense of increasing their probability of a win. We've used tree diagrams to determine the validity of if-then statements back in the Introduction to Reasoning video. Now we'll be using tree diagrams as a tool for assessing probability. Those of you who like to pause the lecture recording to view the videos might pause here to watch the video, The Last Banana. There is also a resource in your module called Probability Tree Diagrams, which is a website you can use to help solidify your understanding of this concept. There are two main rules when it comes to combining probabilities, and these are the AND rule and the OR rule. The AND rule is used when you want to know the combined probability of one plus another event. And when you want to find these combined probabilities, you would multiply their separate probabilities to find the overall probability of those two events together. The AND rule can only be used if the events are independent of each other. In this case, independent refers to the fact that the occurrence of one event does not influence the occurrence of the other event. So an event is considered independent if the occurrence of one does not change the probability of the other occurring. If the events are not independent, you must use a different multiplication add rule. For example, if a bag contains 3 yellow and 4 green marbles, and one marble is drawn from the bag and set aside, and then another marble is drawn from the same bag, you have actually changed the probability of choosing a color of that second marble. So by removing one marble, you've changed the probability, and in that case, the events would not be independent of each other. So in this case, if you wanted to use the AND rule, after drawing the first marble, you would need to put the marble back in the bag before drawing the second marble. The OR rule is used when you want to know the probability of 2 or more different outcomes. When you use the OR rule, rather than multiplying separate probabilities as you do with the AND rule, you would add the separate probabilities. The OR rule can only be used if the events are both independent of each other and mutually exclusive. We've already discussed independence. Mutual exclusivity means that they cannot occur at the same time. That is, both cannot occur. If the events are not mutually exclusive, you cannot use this version of the OR rule. For example, if I asked, what is the probability of a single card being chosen from a deck that is a king or a club? This example would not be mutually exclusive because there is a card that is both a king and a club. Let's do some practice problems using the tree diagram. First, the AND rule. If we wanted to know what is the probability of flipping a coin and landing on heads on the first flip, and then flipping a coin again and landing on heads again. So as you can see in the tree diagram, it starts with that start node. From there, if you were to flip a coin, there'd be a 0.5 probability of landing on heads and a 0.5 probability of landing on tails. Next, on our second flip, there would again be a 0.5 probability of heads and a 0.5 probability of tails. If we wanted to know the probability of heads on the first and second flip, we would use the AND rule, and therefore we would multiply those separate probabilities. So we would have 0.5 times 0.5, which equals 0.25. So the probability of landing on heads on both the first and second flip is 0.25. What about the OR rule? What if we wanted to know the probability of landing on heads followed by tails or tails followed by heads? So first, we need to find those separate probabilities. Heads followed by tails is the same as the practice problem we just did with the AND rule. It would be 0.5 times 0.5, which is 0.25. Similarly, tails followed by heads has the same probability, 0.5 times 0.5 being 0.25. Now, if we want to know the probability of heads followed by tails or tails followed by heads, we add those probabilities, which would be 0.25 plus 0.25, which is 0.5. Let's do a little bit more practice. What if you wanted to find out what the probability is of guessing the correct answer on a 5-item multiple choice test that you know nothing about? That is a completely random guess. Let's start with number 1, the probability of guessing correctly on the first question. So for this, we use our basic probability equation. There is 1 right answer divided by 5 possible answers. So there is a 0.2 probability of guessing correctly, which is akin to saying a 20% chance. In question 2, we take this one step further. We want to know the probability of guessing the first and the second questions correctly. Here we take the individual probability of guessing correctly on the first question, which is 0.2, and we are going to use the AND rule, which means we will multiply the separate probabilities. 0.2 times 0.2 is 0.04. So, whereas there is a 20% chance of guessing correctly on the first question alone, that goes down to a 4% chance of guessing correctly on 2 questions in a row. You could take this another step further if you wanted to find out what is the probability of guessing the first, second, and third questions correctly. It's the same process. Here you would do 0.2 times 0.2 times 0.2. That comes out to 0.008, which is 0.08%. Pretty slim chances. Next, let's move on to the M&Ms example. If you have a bag of M&Ms, and in that bag 5 of them are blue, 4 are green, 4 are brown, and 7 are yellow, what is the probability of choosing a brown or a blue M&M? So here, because we want to know the probability of one or another thing, we use the OR rule, which involves adding. But before we can do that, we have to find the separate probabilities. The probability of choosing a brown is 4 over 20 because there are 4 brown M&Ms and 20 total M&Ms. That comes out to 0.2. Blue M&Ms have a slightly higher probability as there are 5 blue M&Ms out of the bag of 20. And that comes out to 0.25. So if we want to know the probability of a brown or a blue M&M, we would add 0.2 plus 0.25, which would give us a total probability of 0.45. As a reminder, in order to use this OR rule on question number 3, you would need to place the M&M back into the bag before selecting the second M&M. Otherwise, you have violated the rule of independence. A study by Swiderski and Kahneman in 1983, which is discussed at length in your textbook, demonstrated a phenomenon known as the conjunction error. This is what the study involved. The question is, a health survey was conducted in a sample of adult males in British Columbia, of all ages and occupations. It asked participants what they believe is their best estimate of the following values. First, the percentage of men surveyed who had had one or more heart attacks. Second, what's the percentage of men surveyed who are both over the age of 55 and have had one or more heart attacks? I want you to think briefly about how you would answer these. In their study, 65% of the respondents believed that a higher percentage of the men would be both over 55 and have had a heart attack, compared to the percentage of men overall who had had a heart attack. That is, the number was consistently higher for number 2 compared to number 1. This is the perfect example of the conjunction error, which refers to the probability of two uncertain events occurring must be less likely than the probability of one uncertain event alone. We know this because it's essentially an application of the AND rule. The probability of being over the age of 55 and having had one or more heart attacks must be a lower number than the probability of just having had one or more heart attacks. When we use the AND rule, we multiply individual probabilities, and therefore the numbers get smaller. If you think about this logically, taking numbers out of the equation, this should make sense. If only one person in the entire survey was 54 years old or younger and had had a heart attack, right there would be more people in the total sample who had had a heart attack compared to the people who had to be both over 55 and have had a heart attack. Essentially, the conjunction error is simply the erroneous belief that the occurrence of two events can be more likely than the occurrence of one of them. I shared earlier that subjective probability is oftentimes used to determine whether somebody wants to engage in the stock market and or the lottery. And when it comes to playing the lottery, the specific game that is played and the amount of money that is risked. So let's look at two types of lottery games, the Big 12 and the Lucky 7. I want you to read through these examples and decide for yourself what seems to be the safer bet. For the Big 12, it'll cost you $1 to play. If you roll a pair of dice and get a 12, you'll get your dollar back, plus another $24. And if you roll any other number, you'll lose your dollar. With the Lucky 7, it'll cost you $1 to play as well. And if you roll a Lucky 7 with a pair of dice, you'll get your dollar back, plus another $6. If you roll any other number, you'll lose your dollar. Which one are you going to play? The correct answer here, if you're hoping for a win, is to play the Lucky 7. And let's use the expected values equation to see how that plays out. The expected values equation is the probability of a win times the value of a win, plus the probability of a loss times the value of a loss. For the Big 12, the expected value probability of a win is 0.028 times $24 if you win. The probability of a loss is 1 minus 0.28, which is 0.972. You'll multiply that times -1, because you would lose $1. When you do the math here, it comes out to -30 cents, which, if you're only going to play once, might not be such a big deal. But if you played the game 1,000 times, you'd lose $300. With the Lucky 7, the probability of a win is much higher, because whereas with the Big 12, you need a 6 on both dice, with the Lucky 7, there are multiple ways to get a Lucky 7. The value of a win is lower at $6. Then the probability of a loss, 1 minus 0.167, which is 0.833, times, again, -$1. When you do the math here, you end up at 0.169, which means if you played 1,000 times and you round up just slightly, you'd win $170. Clearly much better than losing $300. If you guessed that the Big 12 was a safer bet, you were probably swayed by the $24 win. But it's really important to take into consideration the likelihood of winning, which is determined by the amount of possible outcomes associated with a win. Again, it's much harder to roll 2 6s than it is to roll some combination that adds to a 7. It could be a 1 and a 6, it could be a 2 and a 5, it could be a 3 and a 4, or a 4 and a 3, or a 5 and a 2, or a 6 and a 1. There are 6 different ways that you could land on a lucky 7. Since we're on the topic of gambling, let's talk about subjective probability and the gambler's fallacy. Those of you who like to pause the lecture recording to view the videos might consider pausing here to view the video, The Gambler's Fallacy. Subjective probability refers to a personal estimate of the likelihood of a certain event. Unlike objective probability, which is a mathematically determined statement of likelihood about known frequencies, subjective probability is just our personal sense of how likely something might be. In general, subjective probability greatly underestimates cumulative probability over time. That is to say, that we tend to underestimate the long-term probabilities of events occurring. The gambler's fallacy relates to subjective probability in that it refers to this erroneous belief that chance should be self-correcting, and due to that belief, the subjective probability of various events occurring are misguided. In essence, the gambler's fallacy is the misconception that if an event has not occurred in a while, it's somehow more likely to occur, and if it has occurred recently, it's less likely to occur. Of course, logically we know that chance cannot be self-correcting because it is random. But if we believe that something is more likely to happen, it influences our behaviors. For example, if your friend is playing roulette and she records when each number comes up as the winning number, she records 3, 6, 10, 19. After examining the list, she proclaims that a 9 has not appeared in the last 25 spins, and therefore she plans to bet heavily on 9 because it's more likely to occur. It has to occur sometime, right? What would you tell her? Hopefully, you would tell her that the wheel is random and it cannot self-correct based on earlier outcomes. Although the representativeness heuristic makes us want chance to look random, and we feel that it should look random, random can sometimes come in streaks. Another example of the gambler's fallacy in relation to sports was a research study by Gilovic in 1991. This study is discussed at length in your book, that essentially, Gilovic asked basketball fans whether a player who has made or lost 2 to 3 of their last shots in a row is more likely to make the next basket. 91% said the player that had made their last 2 to 3 shots is more likely. So Gilovic analyzed the data from the entire season of the Philadelphia 76ers. He found that if a player just made a shot, 51% made the next shot. If a player had just missed a shot, 54 missed their next shot. If a player just made 2 shots in a row, 50% were successful on their next shot, which is maximum uncertainty. If a player just missed 2 shots in a row, that number goes up to 53% that the next shot is successful. As you can see, the data shows no evidence that players shoot in streaks, and yet, not only the fans, but even the 76 players themselves believe they shoot in streaks anyway. Another common problem with determining probability is base rate neglect. Let's look at an example. Jack wants to win an obstacle course competition next week. He's 10% sure that he will be chosen to participate in the competition from the walk-on line. And if he does, he's 95% sure that he'll finish in first place. What are Jack's chances of winning? What is your gut answer? is his chances of winning above 95%, somewhere between 95% and 10%, or below 10%? I'll give you the answer in just a bit, but first I want to discuss the base rate. A base rate is an initial or an a priori probability. The base rate is essentially, in our example, 10%. That is the initial probability of what needs to happen for the secondary probability to even matter. If he doesn't get chosen to participate, his chances of winning are irrelevant. Base rate neglect, therefore, refers to discounting the impact of a particularly high or low base rate. In this case, if you'd guessed above 95% or somewhere between 95 and 10%, you fell prey to the base rate neglect. That's because if Jack only has a 10% chance of competing in the first place, at best, with 100% certainty that he would win if chosen, he'd have a 10% chance of winning, because he only has a 10% chance of participating in the first place. Because we want to know the probability of him being chosen and the probability of him winning, we would use the AND rule to find the cumulative probability. Therefore, we would multiply 0.10 times 0.95, which is 0.095, which is 9.5%. That is less than 10%. No matter how high the secondary probability is, it can never overcome the base rate. This is important because it is a major reason why we tend to overestimate success when the base rate is low, and we tend to underestimate success when the base rate is high. Let's work through an example from the textbook on probabilistic decision making. Edith attends a very selective university and needs to declare a major. She is seriously considering becoming an accountant and knows that the accounting department accepts 25% of the students who apply. Of those accepted, 70% will graduate, and 90% of those who graduate will pass the national accounting exam to become licensed accountants. Edith wants to know what her chances are of becoming an accountant if she pursues this degree. So, as we've been practicing throughout this lecture, we are going to use the AND rule to determine the cumulative probability. We need to multiply the probability, first, of her being accepted into the accounting department at all, which is 0.25. Then, the likelihood of her graduating, 0.70. Then, the likelihood of her passing the national accounting exam, 0.90. And of course, those zeros could be dropped. When you multiply those together, you end up with 0.158, which is to say that if Edith were to pursue this degree, she has a 15.8% chance of becoming a licensed accountant. Now, suppose Edith finds out that of the 25% of students who are accepted into the accounting major, 80% of those who start off with a 4.0 become licensed accountants, and Edith has a 4.0. So this shifts the likelihood of her becoming a licensed accountant. What are her chances now? Now, getting into the major stays the same at 0.25. But since she has a 4.0, we know she now has an 80% chance of becoming licensed if she can get into the major. When we multiply those together, we end up with 0.2, which is 20%. Therefore, without the piece of information about how GPA influences success, Edith had approximately a 15.8% chance of becoming licensed. Knowing what we know about her having a 4.0, that goes up to 20%. Note that this can also be solved with frequency information rather than probability. When it is expressed as a frequency, it would be stated as, out of 100 people, 25 are accepted into the program, and 75 are not. Of the 25 who are accepted with a 4.0, 20 will become accountants. You can see how that skips a lot of the math we needed to do when the information was expressed as a probability. Next, let's evaluate our own sense of probability in terms of various events that occur in the United States. For each of these, I want you to briefly indicate which you think is the more likely cause of death in the United States, and then estimate approximately how much more likely you think that is than its paired event. These are based on CDC statistics that were posted as of 2020, though many of them refer to data that were collected over the 3 to 5 years before that. Please pause the recording to complete this in-class exercise. Okay, let's see how you did. For the first pair, heart disease or cancer. Heart disease has a higher probability than cancer. Heart disease affects 647,457 individuals in the United States based on mortality rate, whereas cancer is associated with 599,108 deaths. Strokes versus chronic lower respiratory disease. Here, chronic lower respiratory disease has the higher mortality rate, with 160,201 lives lost compared to 146,383. Unintentional drowning versus asthma are very close, and it's possible that in other years or in other data collections that these numbers might flip-flop. They are very close. However, with the current data, asthma slightly beats out unintentional drowning. Unintentional drowning is associated with 3,536 deaths compared to asthma with 3,564. Alzheimer's disease versus diabetes. Alzheimer's disease is associated with a significantly higher death rate compared to diabetes. Alzheimer's disease killed 121,404 people a year, compared to diabetes with 83,564. Motor vehicle accidents and influenza plus pneumonia. Here, influenza pneumonia beats out motor vehicle traffic deaths, with 55,672 deaths compared to 40,231. Unintentional poisoning compared to unintentional falls. Here, pretty significantly, unintentional poisoning is the more frequent cause of death. Unintentional poisoning killed about 64,795 people per year, compared to unintentional falls that killed 36,338. Lastly, homicide versus suicide. Whereas homicide tends to get more attention, suicide is the more common cause of death. Suicide kills about 47,173 people per year, whereas homicide is at 19,500. One thing that's important to note is that we overestimate the frequency of events that occur rarely, and we underestimate the frequency of events that occur often. If an event is frequent, the occurrence is probable. But the amount of attention that certain conditions and events receive compared to others influence our perception of their probability and therefore our evaluation of their risk. The technical term for this bias and risk assessment is the availability heuristic, which refers to the fact that sensationalism distorts our perception of risk. Events that are more memorable because we've seen them often and or because they are associated with vivid imagery or vivid memories are viewed as riskier than mundane events that do not stick in our memories quite as well. The availability heuristic, therefore, biases our sense of risk because we tend to believe that infrequent events that get a lot of attention, like death by lightning or plane crashes or shark attacks, are somehow much more likely than events that don't receive as much attention, like car accidents. Other biases in risk assessment include the fact that events we believe we have control over are perceived as safer than those that seem out of our control. And the perception is what's important here. It's not really whether we have control or not, it's whether we think we do. Voluntary risk is perceived as less risky than involuntary risk, which explains why people tend to find cosmetic surgery safe enough for those who elect it compared to people who have to have surgery for an event that's out of their control. Natural risks are also perceived to be less risky than artificial risks. Observable phenomena are seen as riskier than events with known risks. These are affected by overconfidence, which is basically the belief that we're better and or more capable than other people. Of course, we can't all be better than everybody else, by definition. But as human beings, we tend to believe that we are better or more capable than other people, which influence us to want to be in control because we think we'll do a better job. This is why people who are anxious in cars oftentimes want to be the driver. Another bias in risk assessment is our tendency to extrapolate based on inaccurate, incomplete, and or inconsistent data. Extrapolation is essentially estimating a value by extending some known value. But extrapolation should only be used when the data is fairly consistent. For example, if over the last 10 years the population grew at a consistent rate each year, you could use that data to extrapolate, that is, estimate the population for next year. But when the information is incomplete or inaccurate, or there's just not enough of it, we should not extrapolate. But unfortunately, we tend to, which means we will make assessments about the future that are based on inaccurate, incomplete, and or inconsistent data. Lastly, biases in risk assessment can be due to misunderstanding statistics, such as correlation versus causation that we've discussed previously, and underestimating the importance of a sufficient sample size. For example, significant differences between groups. That refers to when differences between groups are greater than chance. If the sample size is too small, the differences between groups could be a fluke rather than a real statement of a difference between those two groups of people. Therefore, just because something happened to a few people you know doesn't necessarily mean it's more risky or more probable. The last topic we'll discuss in this lecture presentation is statistical use and abuse. You might consider pausing the recording here to view the video How Statistics Can Be Misleading. Alternatively, you might finish the lecture recording and view the video afterwards. A statistic is a number that is calculated on a sample. And statistics, in general, is the branch of math that utilizes probability theory to make decisions about populations. One important statistic are measures of central tendency, which are ways of assessing averages in a group of values. There are three main measures of central tendency, and they all tell us where the middle of the data lies. The mean is the arithmetic average, which is the most often used measure of central tendency when you add all of the values together and divide by the number of values. The median is the middle number in a chronological list of numbers. It's also known as the 50th percentile. The mode is the most frequently occurring value in a list of scores. The appropriate measure of central tendency depends on the variable or the situation. Whereas the mean is generally considered to be the best measure of central tendency, it's really only the best if the data is normally distributed. It is very sensitive to the presence of outliers, which are extreme scores. In the case of outliers, the median, or perhaps the mode, is preferred. This is also true if it's a skewed distribution. Some individuals will intentionally misuse or misrepresent an average in order to persuade the viewer or listener. For example, in the real estate market, if I wanted you to believe that your house was a bargain, I might compare it to the average price of a home in Orange County. And if I wanted to do that, I would use the mean, which would skew the price of a home upwards because it will have to be affected by $20 and $30 million homes, which are clearly not really the average. What should be used when discussing the real estate market is the median, because the middle value is much less affected by extreme prices of homes compared to the mean. You can see how averages can be represented in many ways, and yet, oftentimes, the specific measure of central tendency that was used is left out of the discussion. When you hear an average number, you want to ask yourself, how was that average calculated, and was that the best way of calculating an average for this situation or this variable? The real estate market is also a good example of inappropriately extrapolating on data. For example, if I wanted to sell you a home and I said, prices are going up dramatically, that might be true, but perhaps I'm only discussing the last 2 months of data, which could represent seasonal change rather than an ongoing trend. The bottom line is that we always want to be weary and skeptical about the use of statistics and to ensure that we are investigating to the extent necessary to really understand where those numbers come from and what they really mean.